Morning, Vandana. Let's wait for 2 minutes for others. Good morning, everyone. Still, we are waiting for the others for 1 minute at least. Only six has joined.
Good morning, sir.
Good morning. What about the others? Others are not joining. What about the previous class? How many were there?
This is our first class, sir.
Oh, okay. Oh, first class is of PCL, I think. 8:45.
Yes.
Only six has joined. Still, we are waiting. Okay, so today, yesterday we discussed everything about generating function. We finished that topic. Now we are starting the next topic, which is recurrence relation. So what is recurrence relation? Uh, you know that the geometric progression, the GP series, So whenever we have a sequence which can be represented by means whose nth term can be represented by n minus 1 of term or the previous terms, then we will say it's a recurrence relation. So suppose we have a sequence like 5, 15, 45, 135, and so on. So we know it's a GP series because the common ratio, we have a common ratio here. If we find out 15 by 5, we get 3. 45 by 15, 3. So whenever we have a common ratio between the elements, uh, we'll get a GP series, right? So this common ratio is nothing but suppose I'm taking a sequence like I'm starting with A0. So common ratio is nothing but A1 upon A0, or we can say AN upon AN minus 1. It should be same for every successive terms, right? So for this sequence, we can create a relation called, uh, yeah, we are getting A1 after multiplying by 3 here. So suppose I'm taking R as a common ratio, so I can write it as AN is equal to R into AN minus 1 for N greater equal to 1. So this relation is called a recurrence relation for this sequence, for this GP series, where R is defined by these numbers, AN upon AN minus 1. So this is called a recurrence relation. So this is a recurrence relation for this sequence. So I can this recurrence relation can represent any sequence having common ratio 3. I can write it as another sequence. I can write like 7, 21, 63, 189. For this GP series also, this is going to be a recurrence relation because R is 3 again here. So one recurrence relation can represent many sequences. Okay. Now, I am talking about the first order linear homogeneous recurrence relation. Okay, so what is first order? In this recurrence relation, uh, what is first order? Whenever we talk about, whenever we represent, what happened? Whenever we represent a term in terms of only the previous term, I will say the recurrence relation is of first order. Only in terms of previous term. No other terms is included. Then I will say it is of first order. What is linear? Here, every term is linear. No means it is of degree 1. Every term, every A is of degree 1. Here, there is no an minus 1 an, the product of an minus 1. These kind of A's. We don't have any product of A's here. So that's why this relation is called linear. Okay. Now, what is homogeneous recurrence relation? If I write this equation as an minus r, an minus 1 is equal to 0. So what I get, I get 0 in right hand side. So in general, the equation of first order linear reconciliation general form is an minus r an minus 1 is equal to fn. Okay, this is the general form of first order linear reconciliation. So whenever we have fn 0, on that case, we will say the equation is homogeneous. So that's why we are writing this equation. We are saying this equation as first order linear homogeneous reconciliation. This one. I hope you got my points. Now I'm erasing the slide, this board. May I? Now, if I talk about the unique solution, the solution of this equation, an is equal to r an minus 1. I have taken one example of a GP series 5, 15, 45, 135. So here I can write A0 is 5. Even if I want to find, I have this relation an is equal to rn minus 1. So what I can write, a1 is equal to r is 5 here. Oh, sorry, r is 3 here, and a0 is 5. A0 is 5. So 5 in 3 into an minus 1. An minus 1 means a0. 3a0. A2, if I want to find, I will write r a1. A3 is going to be r a2. So this is 3a0. If I put the value of a1 here, so I will write 3 into 3a0. That is, I am writing 3 square a0. Here I will write 3 into 3 square a0 means 3 cube a0. So a3 is 3 cube a0. So what's going to be the solution if I find out an? What's going to be the solution? 3 to the power n a0. This is going to be the solution. And a0 we know it's 5. So 3 to the power n into 5. So we have a unique solution of this linear first order homogeneous reconciliation, which is an is equal to r to the power n a0. This solution is unique for n is greater or equal to 1, where r is the common ratio, an upon an minus 1, right? So the solution of the recurrence relation depends only on n. R is constant here, right? It is common for every term of the GP series, and A0 is also constant. So whenever we have, see, whenever we have a recurrence relation, they will give you either A0 or A1. If only A0 is given, then I will say it's an initial condition. And if two values are given like A0 and A1, then I will say boundary conditions are given. Okay. So in this slide, I just discussed the solution of this recurrence relation. Using this example, I generated the formula of unique solution of this recurrence relation, which is going to be this one. An is equal to r to the power n AC. Any doubt? Now you know what is recurrence relation, first order linear homogeneous, and what is this unique solution of this. So recurrence relation is this one. I'm talking about this recurrence relation and the solution of this. Now I will discuss few problems related to that first order linear homogeneous. So let me share the screen. I hope it is visible to everyone. So the first question is, find a recurrence relation with initial condition that uniquely determines the geometric progression. Yes. So first we find out they are asking about the recurrence relation. What's going to be the recurrence relation? It's a GP series, right? What about the common ratio? If we multiply 7 by 2 by 5, I get 14 by 5. Then 2 by 5, I get 28 by 25, and so on. So 2 by 5 is the common ratio. So what's going to be the equation? Equation is going to be an is equal to r into an minus 1. So an is equal to 2 by 5 into an minus 1. This is going to be the recurrence relation, right? And what's going to be the initial condition? They're asking about the initial condition as well. So I am giving a0 is equal to 7. Sorry, a0 is equal to 7. So what's going to be the answer? So the answer will be an is equal to 2 by 5 n minus 1 for n is greater equal to 1, and the initial condition is going to be a0 is equal to 7. So this is your answer in one step, right? Now see the second question. Find the unique solution of the recurrence relation 3an plus 1 minus 4an 0. Homogeneous, linear, right? A1 is 5. So what's going to be the unique solution? Here the equation is 3an plus 1 is equal to 4an. So what about an plus 1 upon an if I find? Uh, an plus 1 upon an is going to be 4 by 3. So they're asking about the unique solution. You know the unique solution. So here r is 4 by 3. So what about the unique solution? An is equal to r into a0, right? Here they have given a1, not a0. So you will have to find a0 first, because you have to put the form value here. 4 by 3 a0. This is going to be the unique solution. So a0 you want to find. A1 is given. How can you find a0? A1 is 4 by 3 a0, right? So a0 is going to be 3 by 4 a1. And A1, A1 is 5. So it's going to be 15 by 4. So A0 is 15 by 4. So you can multiply. Oh, the solution is this, not this one, r to the power n also. An is r to the power n A0. Here I am writing. So An is 4 by 3 to the power n. A0 is 15 by 4. So you can solve this. 3 will cancel out. Yeah, we get 4 by 3 to the power n minus 1 after cancelling. And 5 will come out. So this is going to be the unique solution, which will only depend on n. Okay, so to find the unique solution of this reconciliation, first I found r. R is 3 by 4 by 3. Okay, then I found A0 because A1 is given. So A1 upon A0 is 4 by 3. So I found A0 from this relation. A1 is given. So it was 15 by 4. So the unique solution will be An r to the power n A0. R I am putting 4 by 3. A0 I am putting 15 by 4. And I am solving this. So 4 will cancel out. So 1 power will get reduced here. 3 will cancel out. So 1 power of 3 will get reduced. So n minus 1 power for these two, and 5 will remain here after cancelling by 3. Done. Any doubt? You can write in chat box, guys. I don't want any small amount of doubt because of online classes, whether I am quick or something. I don't want these kind of feedbacks. No doubt, right? Please say something if you are there. I'm waiting for your voice. Kirtana, Talib. As of now means what? No doubt as of now, right? Okay. Now I am moving on to the third question. If Laura invests $100 with 6% interest compounded quarterly, how many months she must wait for her money to double? So here they are talking about compound interest first. She's investing $100, so it's gonna be principal, and she wants money to get double. So this is gonna be the amount. So double of 100 is gonna be 200. So amount is 200. Principal is 100. Rate is 6% compounded quarterly. So they are asking about how many months. So I will convert this rate into months per month. So I will, since they are asking, they are saying quarterly. So I will divide this 6 by 4. So 6 upon 4 is gonna be 1.5. So 1.5 is the rate. If I consider everything monthly, 1.5 is gonna be the rate. Okay, so you know the compound interest formula, amount formula for compound interest. So okay, sharing. So here amount is means PN is 200 and P0, that is principal, is $100. Rate I converted monthly, so 6 by 4 I did. So 1.5 is the rate. Okay, so you know the formula for compound interest, the amount formula, Pn is equal to P0 1 plus R upon 100 to the power n. N is the time. So here, if I put the values, I get R 1.5 by 100, right? So 200 by 100 is going to be 2, and this is going to be 0.015 after division, 0.015, and when I will add this 1.015. So if I take log of this to find n, so log 2 is equal to n log 1.015. So n is gonna be log 2 upon, I know this first value 0.3010, I don't know this value. So this you will have to see. So if I can see from here, yeah, I know the answer of this. Actually, this 1.015 to the power n, if I consider, so 1.015 to the power 46 is some 1.98, and 1.015 to the power 47 is gonna be 2.01. So I wanted 2 only. So at least 47 is required to reach on to 2. So that's why n is gonna be 47. Since I was considering things as quarterly, that is 3 months. So I will multiply this duration with 3 to get the final answer. So 47 threes are 141. So 141 months are required for Laura to get her money double. This is gonna be the answer. So I'm repeating the solution. She wants her money to get double. So amount is 100. Principal, she was investing 100. So principal was 100. Rate was quarterly. So I divided by 4 to get rate monthly 1.5. And then I use this formula to find out n and multiplied by 3 to get the answer. Any doubt in this solution? So this question is present in your this topic because this is gonna be the recurrence relation. Pn, and Pn is depending on P0, that is the initial condition, and only dependent on n. So this is gonna be a recurrence relation. That's why this question is present, is belonging to the recurrence relation. So may I move on now? Just wait for a minute. Now see question number 4. Find A12 if an plus 1 square is 5an square. These are squares where an is positive and a0 is 2. So here the recurrence relation is given, but squares are given. That is, this is not a linear recurrence relation, non-linear. But these kind of recurrence relations can be converted into linear form. Very simple. If I consider an plus 1 or an square is equal to bn into linear form. So I can write it as bn plus 1 square is equal to 5bn, sorry, not a square, without square. Bn plus 1 is equal to 5bn. So this is a linear reconciliation. So you can deal with that. You know the solution. The solution will be bn is equal to 5 to the power n b0, right? So we have to find out b0 only. So from b0, how can we find from a0 definitely? So b0 is a0 square. So a0 square means 4. So bn is 5 to the power n, 4 into 4. So what they want, a12. So I will move on to b12. So find out b12. b12 is nothing but 5 to the power 12 into 4. Okay, so to move on to b, from b to a, so what about a? It's root of bn. So root of, sorry, bn is an square. So uh, yes, so a12 square is equal to 5 to the power 12 into 4. So I will find out a12, take the square root of this. So it's gonna be square root of 5 to the power 12, right? So 5 to the power 6 into 2. This you can find. This is gonna be actual. 3125 into 5, whatever. Okay, this is gonna be A12. Okay, so this is the way of converting non-linear into linear form. Simple, very simple. Converting square into linear form and then find out the solution of this equation. You know the solution. Bn is r to the power n b0, and then you put the value of b0 and find out a12. Okay, any doubt in this solution? Converting non-linear into linear. Okay. Now the last question is order complexity of bubble sort algorithm. So we want to find out the order complexity of bubble sort algorithm. This is one of the application of this linear first order homogeneous reconciliation. No, it's not homogeneous. It's gonna be non-homogeneous. Let me start. So in the fifth example, they are talking about the bubble sort algorithm. You know this bubble sort algorithm. Suppose we have 5 numbers Okay, so you have to sort these numbers. Okay, you have to convert and sort these numbers and convert it into ascending form, ascending order. Okay, so this method will work for that bubble sorting. What you will do initially, you will write your numbers into this form. You know this method, I know. You will compare two elements. You will start from the last two, and whenever you want the smallest number on top, right? So if you compare these two, if the if the previous number is lesser than that one, you will not sort. If the previous is greater than the next one, then only you will sort. Okay, you will move every greatest number to down, or every smallest number to up. That is, whenever the bubble will always try to go up. Bubble I'm saying because bubble, it has light in weight, right? So this smallest number has lightest in weight, you can say. So this bubble is likely to go up. So we compare this for these last two. Okay, so here 5 is less than 8, so I will not sort. The order will be same. Next time I will compare these two. I'm writing like that. This curly bracket I'm using for comparison. So this number is lesser than that, so this will also not sort, right? Next time I will compare these two. Now the next is lesser than that, so it will sort. So 2 will go up. Okay, since it is I'm shorting these two numbers, so I will put arrow like that. Okay, 2 will go up. Now I will compare these two. 2 is lesser than 7, so 2 will go up. So I'm sorting again. So 27958. So 2 is the smallest one, which is on the top now. 1, 2, 3, 4. After 4 comparisons, I get 2 on top. Right? Now I will start from this list, 27958. Again, I will do the same thing, comparison. No sorting, right? Again, comparison will short definitely. 5 will go up. And again 7, 5, if I compare 7, 5, 5 will go up. And then here, if I compare these two, no changes. Two fives. There is no need of this comparison, because this number is the smallest one already. So no need to compare this. So we need three comparisons here. Okay, similarly, you do these comparisons. You will start from this now, and you will bubble up. So how many comparisons are required? That thing you have to count. If I give an as number of comparisons, so for taking this 2 up, the smallest into the top, how many comparisons were required? 5. I was taking 5 elements, and initially 4 comparisons were required to take this smallest one up on the top. Okay, so n minus 1 comparisons will be required for uh, going this smallest one up, bubble up. Okay, so I can create this recurrence relation as an is equal to number of comparisons, total number of comparisons. These are required, right? for the first step, for this step. And for these remaining four numbers to sort, okay, how many comparisons will be required? A n minus 1 comparisons, because n were there. So total number of comparisons were n. So after sorting this one, n minus 1 will get remained. So a n minus 1 comparisons will be required. So what's going to be the recurrence relation? A n minus 1 plus n minus 1. N minus 1 for this smallest one to go up, and a n minus 1 for remaining to be short. So this is going to be the recurrence relation. And you know this, it's not homogeneous because an minus 1 is not 0. It is equal to n minus 1. So this is non-homogeneous, right? Now, how can we find out the complexity of this bubble sort algorithm? You will have to find out an. So how will you find out? If we see the pattern, if I use this relation, if I start from a0, I am taking a0 is equal to 0, the initial condition. Now, if I see a1 is gonna be, put n is equal to 1 here. We get a0 plus 1 minus 1 means a0 is 0. It's gonna be 0. What about a2? A2 is gonna be a1 plus 2 minus 1. So a1 was 0, 0, it's gonna be 1. A3 is a3, a2 plus 3 minus 1. A2 was 1 and 3 minus 1 means 2. A4, A3 plus 4 minus 1. A3 was 1 plus 2 and 4 minus 1 is 3. So see the pattern. A1 is 0, A2 is 1, A3 is 1 plus 2, A4 is 1 plus 2 plus 3. What about AN? AN is definitely 1 plus 2 plus up to n minus 1. Okay, so you know this AN now. You know the sum of n minus 1 terms. Sum of n minus 1 terms is n plus 1 by 2. So in place of n, I will write n minus 1. So n minus 1, n by 2. So order complexity, if I check n square minus n by 2, order complexity is going to be of n square. Means an is equal to big O n square. This is going to be the order complexity of this bubble sorting graph. So recurrence relation concept will work to find out the order complexity of bubble sorting graph. So that's why this question is here in this recurrence relation. Any doubt in this example? I want conversation 5 minutes left only. Any doubt? First, I do sorting. I have given one example having 5 elements. I will start from the bottom and then I will try to make that smallest number goes up. And according to this example, I have created this recurrence relation. N minus 1 comparisons were required for going this smallest one on top. And an minus 1 is for the number of comparisons required to sort the remaining n minus 1 elements. So that's why this recurrence relation is there. And according to this pattern, I have checked the order of complexity. Any doubt? You can open your mic, you can say something. The class is likely to get ended. Okay, so today I discussed first order linear homogeneous reconciliation. Tomorrow we'll move on to the second order. Tomorrow, no, next week. Okay, guys, thank you. You can leave now. I can take attendance online, no problem. Have a nice day. Thank you.